Okay, so I'm gonna start off by showing you how to get to this page again. So that's the page for our course. Now, if you go to course syllabus one more time, I did some revision. That's why I wanted to bring you here again. So if you look here, I did put office hours. So it's gonna be Tuesdays and Thursdays, 5:30 to 6. So 30 minutes before class, just in case you want to go over some homework questions or any concern, anything you want to review. I will be here 30 minutes before class, so we can just catch up on some materials. So that's that. And then I also modified one more thing. So I can also stay after class. Yes, Liana. Uh, if before class doesn't work for you, I can stay after class. So that way you can have me either before or after. So you'll get help. Okay. So going back to this page one more time. If you also look down to the homework section, okay, it's in green, so it's really hard to see. I didn't realize this green is that blurry. So if you look at it, if you complete 80% for each assignment on web work, I'll give you 100%. So just like I mentioned to you on the first day, I just officially wrote it on my syllabus just in case I forget. So 80% completion for each assignment will give you full 100% for the assignment, okay? So just make sure you get that done. And yeah, I wouldn't stretch too much on web work. It could be really confusing sometimes. So that's why I want you to do these zeroth assignments where it guides you how to input answers. So that way you can have at least that assignment done for first 2 days, and then you can start doing chapter 1, chapter 2, and so on, okay? And another thing, you don't want to fall behind when you're doing homework because summer sessions are going to move really fast. Make sure every time we finish a section, you start doing the homework, right? So that way you don't fall behind. Okay, and another thing I updated was the time for the final exam. So that's right here. It's going to take place, hopefully, July 23rd. Time will be 5 p.m. to 7:15 p.m. So 2 hours and 15 minutes, the usual final exam time. And so that will be our final on Blackboard and so on. So I'll give you more details as we go along. So those are the new updates. So any questions on that? Okay, how are you guys doing? Okay. All right, so I'm gonna assume you guys are okay. Again, let me know if you have questions. Now, another thing I want to mention is there's still 3 students haven't done their pre-quiz. You should do that. I think it's closed by now, so you won't be able to do it. But the quiz is found right here under course materials. And then if you click on it, well, it still appears for me, but for you guys, it's already closed. And it had 3 questions, elementary questions, and each were worth 5 points. So that was a pre-quiz. So from next week, you will have a quiz on the same section. Those are going to be counted toward your grades, and they're going to take place after class on Tuesday. I'll time you for 15 to 20 minutes, but you'll see it on instruction how much time you have. So right after class, you'll do the quiz on Tuesdays. Okay.
Professor.
Yep.
Yeah, I had a problem with the quiz. So I believe the last question where you had to type in your answer. I put in like multiplication symbols. I did get the right answer, but the way they wanted it, I didn't get it that way, so they marked it wrong. So for, let's say, the test, the quizzes that will count, will you like ever go back and check to see if we did it right or not?
So what I'm going to do, I'm not going to put a written response because it's very sensitive. I'm just going to give you either multiple choice or true and false.
Okay, that works. Thank you.
Yeah. And another thing, you want to be very careful with your multiple choice because they can be tricky. I'm not a great test taker, but when someone makes a test, you want to make sure they don't trick you. So be very careful how you choose those choices, because I'm not thinking of going back to your work and giving you partial credits for the quizzes. But for the exam, I will do that, but not for the quizzes. So be very careful how you submit your answers. Okay? All right. So those of you who had it wrong for the written response, it's okay. It's not counted toward your grade, so you can kind of ignore all of that. And it's gonna disappear from your Blackboard account anyway, so don't worry about that one. So in grade NJ, it's fine. All right. So any other question, concern before we start? Are we good to start? All right. So I'm gonna go ahead and start our lesson for today. Well, before I do that, I do want to ask you guys one more question. Has anyone taken online course last semester, or has anyone not? So, all right. So looks like most of us have seen this platform, right? Okay. All right. Okay. So just making sure that you guys are familiar with this. And again, if you have any question, always send me an email or speak to me before class, after class. All right, so okay, so I'm gonna go ahead and start our lesson for today. So let's start off with just a brief review on what is expected from you. So I'm gonna go ahead and start writing. So something from calculus you should review. So from calculus, so I believe all of you took calculus 1, 2, 3, or whatever calculus you took in whichever school. You know how to do integration by parts. Okay, so if you're not familiar with it, make sure you review. So know how to do integration by parts. Okay, and then the second thing I want you to, again, briefly review so that you can recall when we do these type of integration is the partial fraction decomposition. So that's another technique we learn in calculus for integration. So these are the two topics that I'm going to have you at least review it from your calculus textbook or some notes online. That way, when we get to the integration part, you know what to do. You don't struggle with it. And then as we go along, I'll give you more detail what you should know from the past, like the power series stuff. That's also from calculus. Maybe review it if you're not a big fan of series. So maybe you want to review power series in the future or over the weekend. Who knows when? Okay, so that's something you should remember. And here's another thing that I also want to mention. So just a sec. All right, so Sadia, you don't like that, but they're fun. Power series are fun for differential equations. The solutions that we write for using power series, they're really nice. So I don't want to scare you guys off. I just want to tell you, know what they are, okay? You don't need to know too much about them. Just know how they look like, what is a power series. Just have a general idea if you want to look it over. But for now, know how to do integration by parts, really good. But no partial fraction decompositions, really good, okay? Now, another thing that you should know, very elementary, the integral of 1 over x dx. What is this integral? Do you guys remember this? So this one, right, so this is ln of x plus c, right? It's an indefinite integral, so don't forget plus c. So this is ln of absolute value of x plus c. And another very common is the integral of 1 over 1 plus x squared. Do you guys remember this one? So if you, again, try to recall from the past, let's see if anyone remembers this. So this one is arctangent. Liana, you're correct. So this is also a very common integration that we'll encounter in this course. This is arctangent. So I'm just going to write tangent inverse of x plus c. And I think this is good enough. I would say know your integrations. Those are very useful one to remember, but there are plenty others. Okay, so having said that, let's move on to our lesson for today. So I'm going to start off just recall what we did last time. So this is from last class. We talked about how to classify differential equations. So we define what is an ODE, what is a P, so know the difference between the two. And then we talked about how to define if a differential equation is linear or nonlinear. And then we talked about how to identify the order of a given differential equation. So that's what we talked about yesterday. And then we talked about if you're given a solution, can you verify that this is a solution or it isn't a solution? So we did, I think, two or one example on that. So that was a brief review on chapter 1. So today I want to talk more on chapter 1, and let's finish up chapter 1. So we're still going to continue with chapter 1. And I want to start off by talking about how do you graph first order differential equation? Very simple case. So we want to look at the graphical representation of first order. ODEs. Okay. So we want to have an idea, what does the first order represent? So if you took your quiz, I gave you a question, what does the first derivative represent, right? So I think most of you got that one right, which is good. So it's the slope, right? We're familiar with this from calculus, that the first derivative represents the slope, and the second derivative represents, whatever, but acceleration and so on, right? But we want to draw the first derivative only, right? Thank you, Aisha. So let me give you an example. So suppose you're given a differential equation, dy dx is a function of x and y. So this represents slope at any given point in the xy plane or two-dimensional space, right? So we can say that this specifies a, a derivative which is a slope at any given point in xy plane. right? So this is also called the slope field. And if you took vector calculus, we are also familiar with the word direction field. Okay, so they mean the same thing, direction field. Okay, let's look at an example. So let's suppose we want to draw dy dx is equal to 2x. Okay, so let's draw the slope field. So first derivative, think of it as a slope. So you can kind of say, oh, okay, this is like m is equal to 2x. So from algebra, we use the notation m to represent slope, right? So instead of writing dy dx, I'm going to think of it as m is equal to 2x. Okay, so my slope is 2x. That means I can pick values for x and y. I can define what the slope at that given point, right? So that's the idea. So let's go ahead and draw this. So here is our xy plane. Okay, and I want to start drawing the slope field. So I'm going to pick some values for x. Now, do you agree that you don't have to, y could be any value, right? Because the slope doesn't depend on y. So we don't need to really plug in value for y. So we can just start picking values for x. So if I say when y is 0, okay, throughout, what is my slope? Well, I can pick value for x. So let's pick x to be 1. Well, let's start off with 0. If x is 0, what is the slope? Well, that's going to be 2 times 0, that's 0. So let's draw the slope of 0. So what kind of slope is the slope 0? How do you draw that? Do you remember how to draw 0 slope? Right, so it's just a horizontal line. So 0 slope, we know it's a horizontal line. So I'm going to draw a tiny horizontal line when x is 0, y is 0. So that's the coordinate. So that's really the origin right here. So that's my slope 0. So I don't know if you can see that, but that's slope 0, just a horizontal line at the point 0, 0. And we're just going to continue this for a couple more points, have an idea of where the direction field is. So let's pick another. So y is 0. Let me pick another x. Let's pick 1. So what is the slope? That's 2 times 1. So that's 2. So when y is 0, x is 1, 0, 1, I have the slope 2. So 0, 1 is the point right here. The slope is 2, so it's a positive slope. So you can think of it, it looks like that. Positive slope, okay? And then just keep going in this way. Now I'm going to pick again y is 0, x is now negative 1. So my slope will be 2 times negative 1, that's negative 2. So at the point y is 0, x is negative 1, the slope is negative 2. Negative slope are kind of going downward. So at this point, I'm going to have a negative slope. Okay, so that's the slope at negative 1, 0, and so on. So you just continue this way for a couple more points. Now, let me pick another point. So what if when x is 0, when x is 0, it doesn't matter what y is, right? M will always be 0. So we have a 0 slope when x is 0, so that's right here. So it doesn't matter what y is, the slope is always 0. Okay. So I can plug more points in. And then when x is 1, y is 1. So that's this point right here. What is the slope at that point? So that's going to be 1, okay? And then when x is 1, y is, doesn't matter, slope is always, right? this one right here. And then you can see the pattern. When x is 1, it doesn't matter what y is, your slope is always 2. So I can kind of generalize that right here. And so on. And then let's look at when x is negative 1. The slope is always going to be negative 2 because it doesn't matter what y is. So we can continue this pattern in this direction. So that's a slope of negative 2 at every value of x equals negative 1. And you can kind of extend this idea and keep going for another point. Let's look at when x is 2. So that's this one. And when x is 2, again, y doesn't matter. The slope will be 4. So it'll be a little steeper than the one before. And then you can just continue this pattern. Something like that. So I'm not doing a good job drawing it, but I hope you get an idea. And then I'm going to pick x equals negative 2, which is this point. So when x is negative 2, again, y doesn't matter because it doesn't depend on it. So the slope will be negative 4. So it'll be a little bit steeper than the one we had before. So something like this. So that's a slope of negative 2 at x equals negative 1. So these are the slope at every given point. Now, this represents the first derivative is equal to 2x, okay? And then if you want to find the solution to this, well, the solution would look, you can have an idea that would look like. So I can say this is going to be one of the solution. So so if I'm drawing it correctly, you can kind of guess that it's going to be a parabolic shape. So something like that. So that could be one of the solution. And then you can just keep connecting more slope field. So I missed one of the line. That's another solution. And then just keep going. So all of these curves, we call them the solution to this differential equation. Now, what if I just want one particular solution? So these are just general solutions, right? Now, if I want just one particular solution, I will have to give you a point, right? So I'll have to give you an initial value. So I'll give you a, say, y of 0. So when x is 0, I can give you, say, 2. Right? So that will give me a particular solution. So that will just be a one curve on this slope field. So that's one way we can represent the first derivative. Okay. And then on chapter 2, I will show you how to solve these equations. So right now we're not going to solve them. We just want to have an idea of how do we view first derivative on xy plane. Okay. So let's look at another example. So this was just the first example. Let's do another slope field. So suppose I give you dy dx is equal to negative x over y. Well, before I move on to the second problem, does anyone have a question on this one? Does it make sense? Okay. All right, so Aisha said yes. All right, so again, let me know, guys, if you have any questions. I'm going to move on to the second problem. So let's do the same thing. Let's draw another slope field. Let's draw so we're just going to plot a couple points, not too many, because this will take us really long time if you're doing it by hand. But we just want to have an idea how would the solution look like to this particular differential equation. So these two, I'm going to solve them later today. So hopefully I'll convince you that the parabola is a solution to the first one. And let's see if we can come up with the second one. So for this one, let's check this out. So again, I'm going to think of first derivative as the slope and see if I can come up with some tiny slope at any given point. So we know m is now depending on x and y. So it's going to vary depending on what x is and what y is, right? So let's see. So let's pick some clever points, okay? So that way we can sort of speed up the drawing. So okay. So let's think about it. If I pick x to be 0, it doesn't matter what y is, the slope is always 0, right? So if x is 0 and y could be anything, right? Because if you plug in 0 over any number in the bottom, not 0, right? Anything but 0, you can have the slope of 0 over, whatever number you pick for y, it will always be 0. So when x is 0, it doesn't matter what y is, the slope is always 0. Well, we know 0 slope is just a horizontal line. So I'm going to draw a horizontal line when x is 0. So these are all the points when x is 0, and it doesn't matter what y is. The slope is always 0, as long as y is not 0. Okay. So now what about when y is 0? What happens? What is the slope? So what do you guys think when y is 0? So if y is 0, the slope is, so it doesn't matter what x is, right? But we have 0 on the bottom. So, right, you have an undefined slope, which will give us a vertical line. Got it. So you guys have that, right? So in the second part, x could be anything, but y is 0, so that means our slope is undefined. So y is 0, so that's just the x-axis. We're going to draw a slope of undefined, which means it's a vertical line. So I'm going to ignore the origin when I draw that red line because it's undefined really. So that's that. And then we have undefined slope. So that's undefined slope. And then of course it extends in both directions. Okay, so we have those two fixed. Now we can just start picking some points, okay? So I want to know what is the slope at this point, 1, 1. So when we have the point 1, 1, m is going to be -1. So the slope is negative. So let's just, something like that, right? Negative slope. And then let's look at this point now, -1 and 1. So -1, 1 will give me the slope +1. So +1, I'll say that looks like a positive slope. And then let's plug in a few more. So let's go to this point right here. So I think you guys have an idea where this is going, how the solution to this would look like. So let's just have a few more points. So let's do -1 and -1. So if I pick that point, my slope would be -1. So that's another negative slope right here. And then the last point I'm going to pick is this one. So let's check one has question. Circle, exactly. So thank you, Liana. You can see that the solution to this differential equation is going to be a circle. So, and I'm just going to give you one more point, the last one, 1, -1. So my slope is 1. So there you go, positive slope. And then you can kind of extend the circle. And again, if you want to make sure you can plot in more points, but you can kind of see that it's going to go like that in this direction and then go like this on this direction. And then just keep going, sort of generalize this. And of course, there are more points that I'm missing, but you can fill those in. But to draw just one particular solution, I am just gonna draw this one. So that's one particular solution. But of course, we have more. So these are all the solutions, the general solution, right? And so on. So hopefully you got an idea. So I'm not doing it right, but so this is how it's gonna look like. This will be more convincing when we actually solve this first order, and we were gonna solve it. Promise, I'm gonna solve it later. Okay, so that's something I wanted to show you, that it's possible for us to draw first order. I wouldn't draw second order by hand because that's not possible. All right, so any questions on this? Right. So, Wasi, do you have a question?
Yes, Professor. The slope is undefined at 0, so shouldn't there be something on the graph that would represent that?
So I have a vertical line right here. It's undefined slope.
Okay.
Yeah. All right, so that's the second example we just did. All right, so that's the conclusion for chapter 1. And you might see some similar question for homework in chapter 1. It's just a brief review. All right, so I'm going to go ahead and move on to chapter 2. So chapter 2, we're going to study first order differential equations, but I'm going to go ahead and start with 2.2 first. Okay, so the section of the assignments on your web work, they're not in order. So I would say follow the order that I'm covering in class. So that way, if I do 2.2 first, you make sure you want to start with 2.2 after you finish chapter 1 from web work. Okay, so yeah, they're not in order. I didn't create them, so I don't know why they're ordered in that way. Who knows why, but it's okay. We can always just look for the assignment and work on them. So we're going to start with 2.2. 2.2, we're going to study separable equations. So the goal for chapter 2 in general is to understand first order differential equations and learn how to solve them. Okay, solve them meaning find a function that will make this statement true. That's what it means to find solutions, right? So we want to learn methods on solving first order differential equation. This is going to be method 1. So I'm going to call it method 1. We're going to study 4 methods. So chapter 2 has 4 methods to solve first order. So I'm going to give you the list right now, and then we'll just go through the details as we go along. So the first one we're going to do is separable. The second method we're going to study is if it is homogeneous, and then you use this method. And then third method we're going to talk about is for linear equations. So this would be specifically for linear equations. So again, linear in terms of y, okay, not x, because we want it to be linear in the dependent variable. So linear equation, we're going to call it the method of integrating factor. And the last method we're going to study will be exact. Okay, so separable, homogeneous, and then linear and exact. So that's the kind of like a summary of chapter 2, where we're headed. Okay, and then we'll do applications. So let's start off with separable method. So what is this method? How do we use it? So let me write it out for you. So if you're given, so if you're given this form, if you have dy dx is equal to a function of x and y, or if you have y prime is equal to f of xy, then the solution would be a function of x. Y equals to a function of x, right? So if you have a first order equal to some function of x, y, we're looking for where is this magical function y that solves this given differential equation. So let's start off with the first method. So we want to know, how do you use this separable method? So suppose you have, so if the ordinary differential equation is separable, well, what does it mean to be separable? It means you can write it as a function of x times dx plus a function, so let's call it another function, g of y times dy equals some constant. So this is one way to separate the variable. If you can write a function of x tagging with dx and a function of y tagging with dy equals to some constant, then we call this equation separable. Okay? Then use the separation of variable. Okay. So once we successfully separate them, second step is going to be to integrate. Okay. And then once you integrate, you have the solution in two order. So you can either write your solution in explicit form or implicit form. So then write the general solution. So you have two forms, explicit or implicit. So do you guys know the difference between these two, explicit solution and implicit solution?
Nope.
So, okay, that's fine. So, all right, so explicit means you can solve for a y, okay? So you would have a solution, y equals, some function of x. Implicit means you have x and y all together. So you have, so I'll just say not solve for y. Okay, so if you remember from calculus, when we did implicit differentiation, you had x and y all together. You didn't have y equals to some function of x. So that's what it means to be an implicit solution. So let's apply these steps to the given differential equation. So I'm going to start off with the one we just wrote out earlier. So we had, so this was the example from above. Let's solve dy dx is equal to, let's check this one, negative x over y. So negative x over y. So we already know how it looks like, how the solution looks like. It's a circle, right? It'll vary depending on what initial condition I give you. So let's see if we can get that. So I want to try out if separation of variable would work for this one. Looks like it is. If you cross multiply, right? So we have y times dy is equal to negative x times dx. So here I have a function of x and function of y. So here you have fy times dy, and here you have a function of x. So yeah, I should use different notation. So just to keep it consistent with what I wrote earlier. So I have a function of y, and here I have a function of x, tagging with dx. So I have successfully separated the variables. Okay, so that's where the word separation of variables really come into play. Well, once I finish separating them, right, I can go ahead and integrate both sides. So we have the integral of y dy is equal to the integral of, I'm pulling out the negative x dx. And then you integrate. So the integral of y respect to y, it's going to be what? So this would be 1/2 y squared is equal to negative 1/2 x squared. And I'm going to put plus c on the right side. That's just the integration constant coming up from the left side and right side. You can just put it in one side. And there you go, you have your solution. Now, for this question, I didn't specify which form I want, right? I didn't tell you explicit or implicit. So you can just leave it in this form, or if you want to make it look better, you can go ahead and solve for the explicit form. So this would be the implicit solution. Now, how would I find the explicit solution? Well, I want to solve for y, right? So we can go ahead and get rid of 1/2. So we have y squared is equal to negative x squared plus 2c. Now here's something you want to keep in mind for this course. 2c is same as just any other constant. Okay? So what I'm going to do, instead of calling it c, we're going to call it just c. So it's okay to call this one just c. So I'm going to rewrite y squared is equal to negative x squared plus another constant c. So it's okay to do that because a constant times a constant is just any other constant. A constant plus another constant is just another constant. So we're allowed to do that. So here's something you want to keep in mind for the future. If you have, say, let's say 2 times a constant c1, you can just call it, c. If you have c1 plus c2, one constant plus another constant, let's call it a big constant c. We're allowed to do these kind of things, okay? Or if you have, say, c1 over c2, so you're dividing two constant, just call it another c. So these are some tiny things that you're going to be taking care of for this course. Andrew?
If we left it at 2c, would that be wrong?
It wouldn't be wrong, but you probably won't find that as an answer choice.
Okay.
Yeah, because we just like to simplify things. So instead of writing 2c, we're just going to call it any general constant. Okay, so we're almost done with solving this equation explicit form. So the last thing I want to do is take a square root on both sides. So we have y is equal to plus and minus square root of negative x squared plus c. So this would be the explicit solution. Okay. So there we have the explicit and implicit solution. So 2 ways you can express your solution. Now I'm going to do a little bit more work on the first solution I got because I want to convince you that it's a circle, okay? So what I'm going to do, I'm going to move the x squared term to the left side. So we have 1/2 y squared plus 1/2 x squared is equal to a constant c. Now, if you again wanted to make it look nicer, you can multiply both sides by 2. So you have y squared plus x squared is equal to, so if you multiply by 2, you get 2c. But again, we said constant multiply with another constant is just another constant. So I'm going to call it a c. So this would be the general solution to this differential equation. And if you look at it, what we did earlier, we kind of drew it looks like. So that's the graphical representation. It's a circle, so x squared plus y squared equals constant. So we had x squared plus y squared is equal to constant. So any questions so far? And if I give you an initial condition, so say I give you a point, 1, 1, that will, so if I give you the point 1, 1, if you plug it into this differential equation, 1 squared plus 1 squared is equal to c, so 2 is equal to c. So then you have this particular solution right here. So the blue would represent x squared plus y squared is equal to 2. That would be a particular solution. So we have the general solution, which equals to a constant c, and then once you get an initial condition, which we're going to be doing later on, you'll have a particular solution. Okay, so there we have it. So any questions on this? Okay. All right, so if there are no questions, let's solve another example. So here's example 2. So let's solve. So again, we're looking for only general solution. So I'm not giving you initial conditions yet. Solve y prime is equal to e to the x minus 3y. So because we're only doing 2.2 right now, so you know this is separable, right? Without kind of guessing. So what I'm going to do, I'm going to go ahead and rewrite y prime using dy dx notation. So we have dy dx is equal to e to the x minus 3y. Now, why is this equation separable? How do I separate the variables x and y?
You can rewrite e to the x over e to the 3y.
Exactly. So I can rewrite the right side using the laws of exponents, right? So it's e to the x times e to the negative 3y is equal to dy dx. And now I claim that this is separable, right? So this is separable. And of course, it is separable because we're on this section of the textbook, so they're all separable. So I can go ahead and kind of play around with this and separate the variables. So again, cross multiply. So you have e to the 3y dy is equal to e to the x dx. So I have successfully separated the variables. I have a function of y with dy and a function of x with dx. Okay. And now the next thing is to go ahead and integrate both sides. So we integrate both sides. And here's when you have to remember how to integrate. So this is from calculus. So what is the integral of e to the 3y respect to y?
Wait, why isn't it negative 3y?
Oh, because so right here you have dy over to the negative 3y e to the x dx. Now, because it's on the bottom, you can bring it on top and make it a positive exponent, right? Right? Laws of exponents.
Oh, yeah.
Yeah, so that's what I did. when I rewrote this. Okay, so the integral of e to the 3y, if you remember, this is 1/3 e to the 3y, right? Integration rules is equal to, again, I'm holding on to the integration constant because I'm just gonna put one big constant, c, at the end. And then on the right side, we have e to the x. Well, that's just e to the x. Now that I finish integrating, I have to bring in the integration constant plus c. And we're pretty much done. You can leave it right here. Or if you want to play around with the multiply by 3, sure, I can do that. So let's multiply by 3. So we have e to the 3y is equal to 3 e to the x plus, now here you multiply by 3 on both sides, so you get 3c, but again, 3c is a constant, so I can just recall it constant c, okay? So we're allowed to do such thing. So there we have our solution to this problem. So this will be the general solution. So any questions on this problem? Now, let's solve initial value problems. Initial value problems meaning you have an initial condition. Okay, so just like we had it for this circle right here, I had a general solution, x squared plus y squared is equals to c. General solution. If I give you an initial condition, meaning I give you a point, so you can plug it in and you can find c, that becomes a particular solution. Okay, so that's what we're going to do now. Let's solve initial value problem. So here's the example. Let's solve the initial value problem. So initial value problem, I will be abbreviating using IVP. Okay, so initial value problem. So there's shortcuts for everything. All right, so here's the initial value problem I want you to solve. So let's do dy dx is equal to 1 plus 2y all over 1 plus x. And here's the initial condition. Y of, let's do y of 0 is 3. So the only difference between this problem and the previous two is this portion right here, where I give you a condition so you can find c. Okay, so this portion is the initial condition. So this will help us to find value for c. So, okay, so once we find the general solution, we'll plug in the initial condition to find that particular solution. Okay, so I'll give you a few seconds to come up with the general solution for this, and then we'll try to work on the initial condition. Okay, so just take a few seconds. Okay, so let's start. I'm gonna go ahead and start working on it. So looks like it is separable, right? So it is separable because that's the section we're working on right now. So easy to tell. So I'm gonna go ahead and separate the variables. Again, I can cross multiply. So I have 1 over 1 plus 2y dy is equal to 1 over 1 plus x dx. So I kind of just cross multiply them and looks like it's separable. I have a function of y in one side and function of x in the other side. Now that we have successfully separated them, we can go ahead and integrate. So now we go ahead and integrate both sides. So integrate, integrate, right. So my integration sign looks weird, but it's fine. So how do we integrate the left side? Is this something you know how to integrate? What's the technique to integrate the left side? Ingrid?
Do you have to use integration by parts?
No, we can avoid that. So you can do it by U substitution. It will work. Okay, so Jay, you're almost right. You forgot something. So this one you can do it by U substitution. Okay, so I'll do the work for the first one. So I'm going to use U substitution because it works. So if you do U equals 1 plus 2y, then du is equal to 2 dy, but I don't have a 2 on my integration, so I'm going to divide by 2. 1/2 du is dy. So that's the U substitution for the first integral we're integrating. So Sadia, you're almost right. So Jay and Sadia, you guys are almost there. So you guys are missing the factor that I have here, which is 1/2, right? So Liana, you got it. So if you were to rewrite this integral using this magical substitution we just made, it's going to be the integral of 1 over u times 1/2 du. So I can pull out the 1/2 and then we have du. So this will just be 1/2 ln in absolute value of u plus c. Well, we're going to reserve plus c for the end. And all of this will just come out to be 1/2 ln of u. Well, u is 1 plus 2y. So that's the left side. Now what about the right side? What's the integral of 1 over 1 plus x? Now this is not arctangent. You have to be careful. Arctangent is, if you recall, it's 1 plus 1 over 1 plus x squared. Exactly in this form, it's arctangent. If it's 1 over x, 1 over 1 plus x, you can do U substitution. So J, yep, that's correct. This is ln of 1 plus x plus c, and Meheron as well, and Liana. Thank you. So the right side we see is just a plain ln of 1 plus x. Again, if you want to see how this is done, you can again do another, substitution, call it a W substitution, and then 1 plus x, and then dw is dx, and fill in the blank, okay? And we bring in integration constant plus c. So there we have it. We have the solution to this problem. And now, so we have the general solution. But we're not done yet with this problem because we have an initial condition. Now we're going to apply the initial condition and find what is this value for C. So now let's apply initial condition. So that's IC. Y of 0 is, what is it? 3. So that will give us, so plugging in x equals 0, y is 3. We have 1/2 ln of 1 plus 2 times 3 plus, well, not plus, ln of 1 plus 0 plus c, and just do some arithmetic to find what is the value for C. So we have 1/2 ln of 6 plus 1, 7 is equal to ln of 1 plus C. Well, what is ln of 1?
0.
Yeah, that's the magical 0. Never forget ln of 0 and ln of E, right? Those are like your best friends. You never leave your best friends. So 0. Okay, so having said that, what is C? So C is this magical value, 1/2 ln of 7. I can remove the absolute value because 7 is a nice positive number. Okay, so we have our solution to this. So our solution to this differential equation is 1/2 ln of 1 plus 2y plus, well, so not plus, equals ln of 1 plus x plus c. Well, c we found it to be 1/2 ln of 7. So that will be the particular solution for the IVP. So let me know if you guys have any questions so far. So that's that. And if we didn't have our initial conditions, then of course, this will be the answer to the problem where we just constructed the general solution. Okay. Okay. So any questions on this? So I want to do one more example before we move on to new materials. So that way you can at least exercise some of the integration technique. So here's another example. So let's solve the IVP. So suppose I give you x times cosine x dx plus 1 minus 6y to the 5th dy is equal to 0, and y of y is equal to 0. Okay, so I'll give you just a minute so at least you can come up with the general solution. So let's take a minute. Okay, so let's start working on this problem. So if you didn't finish, it's fine. Just make sure you can follow along with me. So it's separable, right? I already separated the variables for you. So here you have a function of x times dx, and here you have a function of y dy. So it is separated. So I can just go ahead and integrate both sides, okay? So we're going to go ahead and integrate. So we have the integral of x cosine of x dx plus the integral of 1 minus 6y to the 5th dy equals to 0. Well, integrating 0 is just a constant, right? So why not I just put a constant? So let's integrate the first part, x cosine of x. How do we integrate this? Which method are you going to use?
Integrating by parts.
Yeah, right. So this one is by parts. So let's do integration by parts. So you pick a u and you pick a dv, right? So I'm going to pick u to be x, and then du is going to be dx, and then you pick dv, that will be cosine of x, And if you integrate that, you get sine of x. And then what I like to do to remember this formula, I just kind of cross them this way. That helps me to remember the magical formula for integration by parts. So we do u times v, right? That's the formula. So that's x times sine of x minus the integral of v du. So that's where the other line comes from. So that's sine of x dx. Okay, and what's the integral of sine of x? So the integral of sine of x is negative cosine. Right? Do you guys agree? It's negative cosine? Yes. Okay. Right. So again, don't forget those details. And then the negative negative will make a positive in this case. Cosine of x plus, now let's do the other side. What is this equal to? So here I can just integrate using the simple integration rule. Integral of 1 respect to y, that's y. And integral of the second term, that will be negative 6y to the 6th over 6. So the 6 cancels out. You have y to the 6th is equal to the constant c. So here we have our general solution. Now, because this is an initial value problem, right? So that's the general solution. And now is the part where you plug in your initial conditions. So let me know if you guys have any questions so far. How did I get y from 1 up? So the integral of 1 respect to dy is y. Right? So if you recall, the integral of 1 respect to x, that's just x plus c, right? So if you're doing 1 respect to y, that will just be y plus c. Right? Because if you differentiate y respect to dy, you get 1. So going back and forth. Okay, so let me know if that makes sense. Okay, all right. All right, Aisha. So now we plug in the initial condition, right? So let's plug in. So our initial condition is y of pi equals 0. So x is pi, y is 0. Let's plug those in. So we have x is pi, so pi times sine of pi plus cosine of pi plus y, well, y is 0, minus 0 to the 6th. So it looks silly to write 0 to the 6th, but I'm just showing a lot of work. So well, here you have to remember some pre-calculus, right? So again, don't forget the past. You have to remember pre-calculus now. What is sine of pi? What is this magical number?
0.
Yeah, right? And what is cosine of pi? So Anik, it's not -1. So sine of pi is 0 and cosine of pi is -1. So this is 0 and this one is -1. So we have -1 is equal to c. Okay, so now we write out our solution to this. So we have x times sine x plus cosine of x plus y minus y to the 6 equals to -1. So there we have the solution to this initial value problem. So let me know if you guys have any questions on any of the steps we took. So this course is it's so nice because it makes you think back into calculus, into pre-calculus, into algebra. So it really makes you think a lot. So pretty good thing to brush up on, right? All right. Can I explain dv again? So dv, oh, so the integration by parts, that's what you mean. So here we're doing integration by parts for x cosine x. So when you do integration by parts, you always have to pick, so you always have to pick u, and you always have to pick dv, okay? So u is the part you differentiate, dv is the part you integrate. So I'm picking u to be x, so I differentiate, which is 1, so you get 1 dx. And then dv I pick to be cosine of x, so to get v, I have to integrate. So I integrate cosine, that gives me sine. So that's what happened right here. You're kind of integrating cosine of x dx to get what is v. And then the rest is the formula. This is u times v minus the integral of v du. And then again, you integrate one more time. Integral of sine is negative cosine, so the two negative cancels out, and we have positive cosine. So that's that. Okay. So I hope that makes sense. So there is also a shortcut to integration by parts, but I'm going to give it to you when we get there. But if you want to look it up, it's called Tabular Method. Okay, so if you want to look it up, but I'm going to go over it with you guys when we do more complicated integration by parts. Right, so Sadia, you wrote that over there, Tabular Method. Yep, absolutely. So you can use that too. So I'm going to give you one more problem before I move on to the second method. So let's do this question. So here's another example we can work on. So so given the differential equation, dy dx is equal to 1 minus 2x times y squared with the initial condition y of 0 equals negative 1/6. Okay, and so here are the questions to this problem. So A, find the particular solution. Well, let me say it this way. Solve the IVP, right? So you'll find the particular solution. So first part is to solve the IVP. And then for the second part, so for, let's see. So while you find the solution to this, let me think about how I'm going to word the second part. So I'll give you a minute to finish this one. So right, Sadia, you're correct. So tabular method, there is a reason when we use it, and there is also a reason why we don't use it all the time, because there's a price for everything. So I would like to use tabular method when the function you pick eventually goes to 0 when you differentiate a couple of times. That's the time. So if you know how tabular method works, you know what I'm talking about. If you don't know what I'm talking about, it's okay. You can ignore and just work on the problem I just wrote down. So it's on the screen right now, but here's the problem. But I will go through the details of using tabular method when we get to more heavier on integration by parts. So don't panic, it's okay. We're gonna get there. So for the second part, I want you to determine, let's do determine the interval. in which the solution is defined. Okay, so let's find the solution to the IVP, part A. So it is separable, right? Because that's the section we're on. So it's funny, right? But when we get to 2.9, when you're going to have all the different first order thrown into you together, you have to decide which method is applicable. So, but for now, it's separable. So let's go ahead and separate the variables. So part A, I'm going to separate them. So we have, so again, cross multiplying looks like the best option. So we have y to the negative 2 dy is equal to 1 plus 2x dx. So I have successfully separated the variables, and now I'm going to go ahead and integrate. So let's integrate both sides. Okay. So when I integrate y to the negative 2, yeah.
The value should be 1 minus 2x.
1 minus 2x. Oh, yes. Thank you. Thank you. Appreciate it. All right, so typo from my side. Okay, so I think it looks okay now. All right, so if I integrate the left side, I have negative 1 over y is equal to, and on the right side, I have x minus x squared, and now I can bring in the constant c. Okay, so that's my, that's how the solution looks like. Now I'm gonna just play around with the solution and make it look nicer, but you can go ahead and plug in your initial condition right here because you already solved it. But I'm just gonna play around with the negative sign and for y as well. So we have y is equal to 1 over x squared minus x plus c. So again, negative c, positive c, you can just call it a positive c. And now I'm going to impose the initial condition. Y of 0 is negative 1/6. So if I plug these in, I have negative 1/6 is equal to, so x is 0, so we have 1 over 0, 0, c. So that means c is equal to negative 6. Okay, so we have our solution to part A. To our particular solution to this, it's going to be y equals 1 over x squared minus x minus 6. That will be the solution for this problem. So any questions up to this point? Okay, now for the first part, for the second part, we want to determine the interval where the solution is defined. Okay, so we have the solution. Now, because the solution, if you were to draw this on xy plane, we can draw it. We have enough knowledge to draw this. It's a rational function, right? So that means there are values for x when this solution is undefined. So we're going to go ahead and find those values. So I'm going to go ahead and, practice some factoring. I'm going to go ahead and factor the bottom. So we have y is equal to 1 over, so you guys remember how to factor? X squared minus x minus 6. Right, Aisha? Thank you. So this is taking us back to pre-calculus. How do you factor? Or algebra, wherever you studied factoring. So I'm going to guess and check. X minus 3, x plus 2. I think that will do the job. Yep, this works. Right, so Aisha and Liana and Anik, you guys got it. So good job. I'm going to go ahead. So we know the solution exists everywhere except when the bottom is not 0, right? So this solution, we know x cannot equal to 3 because that's when the first factor is 0. and x cannot equal to -2 because that's when the second factor is equal to 0. So let's find the interval when this is defined. So I like to draw the domain, as I like to call it, on number line. So here's the real line, and here's -2, and here's 3. So open circle at these endpoints because they're not part of the solution. And everything to the left of -2, in the middle, and to the right of 3 is satisfied, right? So in interval notation, we can say -infinity to -2, u. U is for union. I hope you guys remember that. -2 to 3, union 3 to infinity. So that's where this particular solution is defined. But we want to know what is the initial condition defined, right? So initial condition is, so the initial term, well, initial. So we look at the initial condition, which is y of 0 is -1/6. So which interval does this condition fall into out of the 3 that we just found? So we want to know, where will this initial condition fall into?
Isn't it between -2 and 3? Like the middle?
Yeah, exactly. So we're going to say that the answer to the second part, the solution is defined on the interval -2 to 3. So that would be the answer to this question. Okay, so yeah, kind of summarizes everything for us. So interval notation, factoring, and then writing out the solution as well. Okay, so that's the answer to the second part of this problem. So that will conclude the method of separation of variables. Any questions? So it's not because of -1/6, it's because of the initial term, which is 0. So we're looking at, so right here, we're looking at 0, this one. So this point, let's call it T naught. Okay. Well, actually x naught in this case, because we're using the variable x. So sorry, I'm using so many different notation. I shouldn't do that. So the initial condition, but it falls into that interval. Okay. So any questions? All right. So Liana, you got it. So that's the end of separation of variables and some examples that I worked through with you. Now the next method we said we're gonna talk about is, so separation of variable is check. Homogeneous. So homogeneous, the term applied to first order, is different for applying to higher order differential equations. Okay, so for first order, this is what it means to be a homogeneous equation. Okay, so this is the second method. So we're still on 2.2. This is the end of 2.2. Method number 2 is homogeneous. So only in this section, first order homogeneous. ODEs. So homogeneous has different meaning when we go to chapter 3. Okay, so for chapter 3, homogeneous means when you set the equation equal to 0. But for this section, homogeneous will have the following meaning. So if we have first derivative is equal to a function of x and y, we can and so we have this and can be rewritten in the following form. So dy dx is equal to a function of y over x. Then we call it homogeneous. Okay, so if you have a first order differential equation and if you can rewrite it as a function of y over x, then we call it a homogeneous equation. So I'm going to give you an example to illustrate this idea, and then I'll give you steps on how to solve these particular differential equations. Okay, so that's how I'm going to start. So suppose I give you this differential equation. So suppose you're given, so let's call this an example. Say you have dy dx is equal to x squared plus x times y plus y squared over x squared. So you have a differential equation as a function of x and y, okay? So that was the first statement I gave you right here. I have a differential equation as a function of x and y. What I want to do is I want to rewrite it in this form, a function of y over x. Okay, so that's what we want to do. But before we do that, we can simplify. Always simplify if you're able to. So I'm going to go ahead and divide each term by x squared. So we have the following. dy dx is equal to, so I have x squared over x squared plus xy over x squared plus y squared over x squared. Okay, and this would simplify to 1 plus y over x plus y over x all squared. So do you see how we were successfully able to rewrite it as a function of y over x? Okay, so that's the magic about this. Well, no magic, it's just simplifying, okay? So we were able to rewrite the derivative equal to function of y over x. Okay, so once I'm able to do that, well, then we call it this is homogeneous. Right, first order. So what do we do if it is homogeneous? Well, once you have discovered it is homogeneous, we're going to use this magical substitution. So we're going to use a variable. We're going to use the substitution so I forgot how to spell this word. I think that's how you spell it, substitution. Okay, ignore my spelling. I think I'm not spelling it correctly, but we're going to substitute this new variable v is going to replace y over x. Okay, so v is a function of x. If that's the substitution, we have to come up with the substitution for dy dx, right? So right, so we have d equals v times x. So if I do that, well, what is the expression if I differentiate x? Then dy dx is going to be.
Your mic is cutting out.
Oh, okay. So let me reset it. All right. Hello, hello, hello. I hope it works now. Is
Yeah,
it better?
seems better.
Okay.
I think
All
so.
right. So okay, let's hope it's okay. It's good. All right. So we have very little minutes left, so I'm just gonna see how much I can finish. But so the idea is once you're able to rewrite it as y over x, then you introduce this new substitution, which is going to be v is equal to y over x. That means I need an expression for dy dx, right? How would I replace that? So you differentiate respect to x. So because v is a function of x, so right, v of x is a function of x. So it's not a constant. So that means to differentiate this, you have to use product rule, okay? So by using the product rule, I'm going to differentiate vx. So differentiate x, you get 1. So that's v plus, and now I keep x, differentiate v respect to x. That's dv dx. So that will be the substitution we're going to use in place of dy dx. So these are the two factors you have to remember. Okay, so now that I have come up with this substitution, I come back to my original differential equation and I'm going to replace them. So dy dx will be replaced with this expression, v plus x dv dx, and then y over x is going to replace with v. So we have 1 plus v squared. So let me know if you guys have question with how I transform xy into vx. Okay, so everything in terms of v and x. Now, once you're in this stage, this equation is separable. So this is separable now. Okay, so we're gonna try to play around with this and try to separate the variables. So I'm gonna go ahead and subtract v from both sides. So v will cancel out. So we have x dv dx is equal to 1 plus v squared. Okay, and now I can play around with this a little bit more and separate the variables. So we have 1 over 1 plus v squared dv, so is equal to 1 over x dx. Now, do you see it is separable? So on the left side, I have a function of v tagged with dv, and on the right side, I have a function of x tagged with dx. Now I can go ahead and integrate the fun part. This is when the fun begins, right? More fun, right? You're doing a lot of work, and then all of a sudden it's separable. So you're like, aha, let's do separation of variables. Well, now the integration is pretty familiar to us, right? What is 1 over 1 plus v squared? What is that integral?
Arctangent of v.
Yep. So this is the famous arctangent that you never forget. So I'm going to write tangent inverse of v plus, so not plus, equal. And 1 over x, that's again another famous one you have to remember. This is the ln of absolute value of x plus c. Well, we have finished integrating, but hey, we want the answer to be in x and y. So you bring back the substitution you just made, v is equal to y over x. So now v is equal to y over x. I'm going to substitute this back. So we have tangent inverse of y over x is equal to ln of x plus c. So everywhere I have my variables that I wanted, x and y. So that will be the solution to this differential equation. So that's how you use the method of homogeneous. So the only time we can use it if the equation is homogeneous. Okay, so let me write down, how can you check if the given equation is homogeneous or not? So here is a rule to check. So again, let me know if you guys have questions. So how to check if an ODE is homogeneous. Okay, so that's the big question. Well, how do we know? So there's always a rule. So if you're given a differential equation as a function of x and y, where it is not separable. So at the beginning, it's not separable, but then it becomes separable, okay? And it's not linear, so not linear. I'll talk about linear next time. So we want to check the following. You want to check if you do the following substitution. So if you substitute x times k and y times k, you get back the original equation, f of x, y. So we're going to substitute x with k times x and y with k times y. And if you get back the original equation, f of x, y, then it is homogeneous. So let's check, okay? So why is it that this equation that I give you is homogeneous? Well, I just give it to you because I give it to you, right? But let's check. Right, you don't trust anyone. You always want to check yourself. So I want to test if this is homogeneous. So test if it is homogeneous, okay? So I'm going to substitute x with k times x, and I'm going to substitute y with k times y. K is just any constant, okay? You can see if you want to, but let's keep it as k. So we have this. We have dy dx is equal to, so if I substitute k times x for x, we have k squared x squared plus x times y. That's k times x and k times y plus y squared. Well, that will be k squared y squared all over x squared. That's k squared x squared. Okay, and then you try to simplify and see if it gives you the original equation that was given to you. So let's hope it does, right? So it looks like I can factor out k squared from all of the term on the top. So you have k squared times x squared plus xy plus y squared, everything over k squared and x squared. Now, do you agree that this is the original equation you had? Right? These guys, they cancel out. So you have the original equation. So here's my function of f of x, y. So check. So that's why the method I just used, it works, because it is an homogeneous equation. And if you try to use the separation of variable for this example, you can't. There's no way you can isolate x and y. So we have to find another method. And somehow, magically, homogeneous happened to work. And if you also test, is it linear? Do you agree that this is a nonlinear equation? Do you guys agree?
Yes, because the y is being multiplied by x, or
Not because of that. Y squared.
Oh yeah.
Right? That's why it's nonlinear. All right, so I did do an example for homogeneous, but I didn't really give you the steps. So I will summarize the step next class, but you can still start doing your homework for chapter 2. So the steps are really here. You come up with the substitution, and then you redefine what is dy dx is, substitute everything back, and then from there it's separable. So I hope that makes sense.
Professor,
All right.
can I ask a question? I just wasn't sure how you got to the dy over dx equals v plus x dv dx. I don't know how you.
Okay.
Yeah.
So that's coming from this part. So if you, so I'm differentiating this respect to x.
Okay.
So by using product rule, right? So here's a side note.
Oh, product rule. Okay.
Yeah, do you see it? So
Yeah.
y prime, it's going to be, so you keep the first function, differentiate the second, derivative of x respect to x is 1. Plus, now you differentiate the first function, keep the second, so I keep the second, and the derivative of v respect to x, that's just dv dx. We don't know what v is, so
Yeah.
that's how I
see.
got that part.
Okay. Thank you.
Yeah. So you can either memorize this, that dy dx is always going to be those terms, or you can just simply keep differentiating using product rule. So I wouldn't memorize it because there are other things that you want to memorize, not this, which are coming up in the future. Okay. All right. So for homework, start with the 0th assignment, move on to 1, start working on chapter 2.2 as well. Okay. So I will see you all tomorrow, and thank you for coming and joining me. Stay well until then. Do you guys have any questions? Andrew? You're welcome, guys.
Professor, when's the homework due?
Good question. Let's find out.